more to do. And I think controllers need to move toward this direction going forward. No question in my mind about that. We'll see if it takes 10 or 20 years to happen. Okay, I want to talk about simulating memory here also. If this were a long course, we would have assignments in terms of simulation. I think this is really important. Or evaluating new ideas for new architectures in general. I have this lecture on simulation that I give sometimes in my computer architecture course. I'm going to give part of that over here. So basically, the key question is, how do we assess an idea will improve a target metric X, right? That's what we're really interested in the end. And we have many potential evaluation methods to answer this question. Theoretical proof is one example. Analytical modeling and estimation. Simulation at varying degrees of abstraction and accuracy. Prototyping with a real system, for example, FPGAs, or a real complete implementation of the idea as it's expected to behave in real life. And this clearly is a huge range, right? These are the methodologies that are available to you. In architecture, the architect's dilemma is which one to use. Usually, this one is not available to the architect because the things that we're examining is real workloads, real systems. It's very hard to prove things about them because, first of all, it's very hard to formulate them in a mathematical, theoretical manner, except for very few cases. People have tried to do this with caches, for example. All of the theory in caches have some theoretical mechanisms, very hard to prove, but they try to model things in some way, but it doesn't work very well, even in the constrained case of caches. So modeling the workload is a very difficult problem. Analytical modeling and estimation, this is also done. That's not the topic of this. If you can do this, that's great. Of course, there's always the danger of, are you actually doing things correctly? We may talk about that later on. So architects usually use one of the evaluation methods that are down over here. This is not always easy, as you can imagine, right? Real implementation, it requires a lot of effort, a lot of resources, and even the real implementation may not be real, especially in DRAM, for example. If you want to evaluate a new DRAM architecture, if you really want a real implementation, you need to have a process that's compatible with what Samsung or Hynix is doing, cutting-edge technology. And clearly, if you're a researcher, you may not have all the resources to be able to do that. In fact, you're far from it. So this is actually not as easily accessible to many researchers also. So usually are stuck between these three things. And simulation is the most flexible one. And that's actually one of the most important ones because this enables you to do a lot of things. So we're going to talk a lot more about simulation. So the answer is usually workload-dependent architectural evaluation, caching, for example, pipelining, any idea we talked about in some lecture. We may talk about more. Workloads change, and system has many design choices and parameters. Architects need to design many ideas and many parameters for a design. It's not easy to evaluate all possible combinations, right? So that's why it's not easy to evaluate. And also system parameters may change. You're actually designing some system that's going to be used 5 years into the future, and maybe it can last 10 years in its lifetime, right? You may not even predict what the workloads that are going to be executing on this will be, right? So how do you actually do the evaluation? Okay, so that's why architects resort to simulation quite a bit. This is really the field of dreams also, right? Like every dream, it could be a good dream or a bad dream. It could be a pipe dream. We'll see. So basically, an architect is in part a dreamer, a creator, right? And simulation is a key tool of the architect. It enables many, many things. It enables the exploration of many dreams. For example, reinforcement learning-based memory controllers or different memory scheduling policies. How do you do that? Well, you could build machines that actually implement them, but it may not be a good idea, right? That's very costly to explore some ideas that may never pan out. So simulation is doing all of that in software, which is a very good idea because it's not very costly. It can be relatively quick. It enables the exploration of many dreams and many different parameters. It enables a reality check of the dreams also if it's done well, because your simulator can be very well checked and you design it with the best principles in mind. Of course, this requires some experience as well. It enables you to decide which dream is better, which memory controller is better, but also enables the ability to fool yourself with false dreams. So you need to be very careful in simulation. If your simulator gives you the wrong answer, or you should do this as opposed to this, in reality, In reality, if a reinforcement learning memory controller is going to be much worse than an existing controller, and if your simulation is not able to show you that, then there's a problem, right? Okay, so high-level simulation is necessary because you need to explore these many dreams, basically. RTL simulation, which, how many people here have done RTL design? Okay, in Verilog, VHDL? Okay, Verilog, VHDL? Isla is Verilog. Okay, but some people actually raise their hands with VHDL also. How many people have done higher level simulation, like C, C++? Okay, okay, that's good. That's a different kind of mix. So RTL simulation is very low level, basically. You actually generate every single gate, and it's intractable for design space exploration because it's too time consuming to design and evaluate things, especially over a large number of workloads. This is just not possible to do a simulation, especially if you want to predict the performance of a good chunk of a workload on a particular design. And the design space quickly explodes over here. By the way, machine learning techniques actually are very interesting to explore in this space as well, especially if you want to consider many design choices. This is one example, just in terms of caches, right? Cache size, associativity, block size, algorithms. But cache is only a small component of a processor today. There are many, many components. Memory control and scheduling algorithms that we've discussed, some of them, in order versus out-of-order execution. And once you go into out-of-order execution, all of these different parts of a machine, if you want to simulate all of them, then you have a problem, right? So the goal in high-level simulation is to explore the design choices quickly to see their impact on the workloads we're designing the platform for. And there are different goals in simulation also. One is exploring the design space quickly, as we just said, and see what you want to potentially implement in a next generation platform or propose as the next big idea to advance the state of the art. And the goal is mainly to see the relative effects in design decisions to begin with, because you're not really implementing the system, right? You want to, in most cases in research, we're concerned with the relative effects. How large of a relative effect do you have, and is that relative effect real? Is a reinforcement learning memory controller much better than an existing system? Maybe you don't care about 10 to 20% as much at this point in time. You just want to get an idea of, is this a good idea to pursue, really? That's one goal in simulation, right? And this is a really important goal, especially if you want to advance the state of the art, as I said over here, right? Another goal could be match the behavior of an existing system so that you can actually debug it and verify it at some level of accuracy. This is to actually calibrate your simulator such that your simulator models the system really well, such that you can enable the debugging of the system, right? Or propose small tweaks to the design that can make difference in terms of performance or energy. If you have a really good simulator that actually models your existing system really well, then you can actually propose tweaks, and then you can incrementally improve the design. And this is also very important, but a very completely different goal compared to exploring the design space quickly. In this case, the goal is very high accuracy, as you can see. You want to be very accurate in your simulation such that whatever you propose actually is going to improve the system at hand. Whereas here, you want to see the relative effects so that you can take the next big leap forward. And there could be other goals in between, clearly. This is very high accuracy. This may not be extremely high accuracy. Here, you care about 0.1% perhaps. Here, you may not care about 0.1%, basically. So you may actually refine the explored design space without going into a full detailed cycle-accurate design. That's another goal in between. Coming from here, you basically go to the next level. Or gain confidence in your design decisions made by the higher level design space exploration. So we could actually expand this. But there are trade-offs in simulation also. And that is actually those trade-offs that you make in the design of your simulator is dependent on your goal. And there are three metrics in simulation. It's obvious. One is performance or speed. Second is flexibility. I put second over here, flexibility. And the next one is accuracy. And you don't usually get all of them at the same time. If you want to build a really accurate simulator, you have to usually give up flexibility and speed at the same time. If you want to have a very fast simulator, you can actually make it flexible, but you usually give up accuracy, basically. And if you want a really flexible simulator, you may or may not give up speed, but you're likely to give up accuracy. Although this depends on where you are in this. You're matching the behavior of an existing system. So it depends on the flexibility also, what kind of flexibility you have. So the highest level of flexibility is, of course, like you can simulate everything that comes to you, right? So speed is how fast the simulator runs. For example, how many instructions per second you can simulate, how many cycles per second you can simulate, how many requests per second you can simulate, in case of memory, perhaps. Or what is the slowdown compared to a real system that runs this particular application, right? You can actually measure it, measure the speed of the simulator compared to a real system that runs the real workload also. So there are different measures over here. Flexibility is how quickly can one modify the simulator to evaluate different algorithms and design choices. This is also important. This enables you to quickly explore the design space, as you can see. And accuracy is obvious. How accurate is the performance numbers that the simulator generates are compared to a real design? This is also called the simulation error, basically. Of course, this may not always be easy to determine, right? If you're actually targeting a future design that doesn't even exist yet, so how do you actually evaluate the accuracy of your simulator compared to that future design? Not easy. If you already have an existing design, and if you're building a simulator for it, the simulation error is easy to determine. But if your design is going to be completely different, let's say processing in memory, that doesn't exist yet, how do you evaluate the accuracy of your simulator? How do you validate it? Not that easy, actually. This is where a lot of art and experience comes in my opinion. Yes?
Just a good comment on accuracy. There's the absolute accuracy and relative.
Yes.
For example, if you want to tweak, you don't care whether it's accurate, you want absolutely accurate, you want to make sure that if it shows an improvement of 1%, it is an improvement of 1%, though both may be off relative to the accuracy.
Yeah. So I think, this goes back to what you said is absolutely correct. It goes back to what is your goal, right? If your goal is to actually improve the system, and your decision is not necessarily based on 1% or 1.1%, then yes, relative is important. But if your decision is really dependent on, oh, I have this costly mechanism, am I really going to get 1% out of it? Then you may want to be really accurate. So it really depends on your goal, I believe. But I agree. Fundamentally, there's a different types of accuracy, like relative versus, Okay. So the relative importance of these metrics varies depending on where you are in the design process and what your goal is, clearly. So this is really not a full science. There's a lot of art in simulation. And I think this is really the fascinating part of simulation also, because it enables the exploration of dreams, but you've got to be very, very careful in doing this. And it's usually a trade-off, as I said. Speed, flexibility, and accuracy. Speed and flexibility affect how quickly you can make design trade-offs, clearly. Accuracy affects how good your design trade-offs may end up being. And also it affects how fast you can build your simulator. So simulator design time is something that I didn't put explicitly into the previous slide, because that's another thing, right? Because it's not it's not like an output of the simulator, but it's really something that is important still. And if your simulator takes too long to design, that's a downside also, right? That actually affects how quickly you can make design trade-offs in a different way. Flexibility also affects how much human effort you need to spend modifying the simulator. I've seen this actually many, many times. There are a lot of simulators that are out there that are not flexible enough. So you actually spend a lot of your effort to first understand and debug the simulator. And you can, as I said, you can trade off between the three to achieve design exploration and different design exploration and decision goals. So high-level simulation, the key idea is to raise the abstraction level of modeling to give up some accuracy to enable speed and flexibility. That's the explicit trade-off in high-level simulation. And of course, quick simulator design comes with it, hopefully. The big advantages, well, like everything else in the world, it has advantages and disadvantages. Maybe I'm biased over here because I dedicate a lot of space for the advantages over here. But I'm a big proponent of high-level simulation because it's necessary for big advances in the world, no question about that. So you can still make the right trade-offs and do it quickly. So you need to be very careful about this last disadvantage, of course, right? If this disadvantage can destroy all of the advantages over here. The other advantage, all you need is modeling the key high-level factors, and you can omit corner case conditions, and that's how almost all high-level simulators are really designed. Of course, what do you omit? What do you not omit? This can come back to bite you very significantly, depending on your workload as well. So this requires a lot of experience, but also a lot of care as well. So this is where art comes in a lot. And all you need to, as we just discussed, all you need to get is to get to the relative trends accurately, not accurate exact performance numbers, because that's not the goal in general in high-level simulation. Of course, the disadvantage is this. It opens up the possibility of potentially wrong decisions, right? Because you're off in the dream space somewhere, and you don't necessarily have a ground truth anywhere over there, right? How do you ensure you get the relative trends accurately? This is an open question. No question about that. So simulation as progressive refinement, I like this also. And it's good to do this as much as possible. Basically, you have real design at the bottom, ground truth, and high-level models. By the way, real design may not be what you really want also, but at least it's the ground truth of what exists. And you have high-level models. And you can go both ways, right? You can actually start with a real design and construct this. Usually it's not done that way. But usually you start with some high-level model of what you want to design and explore the design space over here. And then once you're comfortable with some of the design decisions, you generate some medium-level models, more sophisticated, slower, less flexible, less abstract. And then once you're comfortable with some of the design decisions, you go into lower-level models, RTL with everything modeled. And then after that, maybe you decide to implement the design and you get a real design. Maybe you prototype it somewhere in between. Clearly, there are errors between these. Even the RTL doesn't match the real design. That's not necessarily. Because RTL is simulation also, right? It's not real life. And people actually try to calibrate RTL with real designs in many companies. So that's obviously, there are errors over here, but at least it's one of the closest things to the real design. But as you get over here, so it's a progressive refinement. You go from up to down. But once you have the real design, you can go from bottom up and refine your simulators also so that they're more accurate to your real design. And you have more, now you become more confident in your higher level models as well. And then that could enable better exploration over time. So it's really a progressive refinement over time, especially after you get to the real design. So as you refine, go down the above list, abstraction level reduces, obviously. Accuracy hopefully increases, not necessarily if you're not careful, because this model may be less accurate than a high-level model. And actually, I've seen this many times also. For example, in power modeling, sometimes higher-level models are better than medium-level models. If you count everything and then try to give it a power cost, and then have a huge equation, that may be less accurate than counting the biggest events and actually correlating that with your power. So as you refine, flexibility definitely reduces, and speed likely reduces, except for the real design. Once you have the real design, it's baked into hardware. It's not software anymore. So speed is probably the fastest, actually, right, over here. And then you can loop back and fix higher level models, as you can see over here, as I said, actually. So making the best of architecture is actually being comfortable at all levels over here. A good architect is actually comfortable at all levels of the refinement, including the extremes, real design and the extremely high-level simulation. And it's good to know when to use what type of simulation, clearly, right? And more generally, what type of evaluation method, not just simulation. There's the analytical model that we didn't really discuss that much. That's also very, very important. Sometimes you could actually think of analytical model as an abstraction level beyond the higher level simulation. And that could actually enable you to quickly prune the design space in a much better way. So, yeah. I think I'm prefetching what's coming in the slides, as you can see. Okay, given that, so this is basically the simulation. I think it's really important. It's good to be aware of it. I'm going to talk about the simulators for memory, but only one particular simulator. We've developed a lot of simulators for memory, and the open source codes that I mentioned earlier actually list a lot of those simulators. You can find them online. Ramulator is one of the latest incarnations of this. It's actually alive. It's being developed. It's being used by many companies as well as academia. And companies privately or sometimes publicly report the bugs in them, and we fix the bugs. So it becomes much better over time. And if you're interested, you can take a look at it as well. So our goal here was high-level simulation, but accuracy as well at the same time. So DRAM and memory control landscape is changing, as I said. There are many new and upcoming standards and many new controller designs. We wanted to have a fast and easy-to-extend simulator that could model a lot of these standards in a flexible manner. I'm not saying this is the best simulator out there, but this is better than what existed before. I think now we're seeing a lot of the downsides of it also, so we may have another incarnation of it at some point. But basically, Ramulator provides out-of-the-box support for many DRAM standards. As you can see, many things over here. At the time it was released, it was 2.5x faster than the fastest open source simulator. And there were a bunch of open source simulators, as you can see over here. And one of the key design choices was to make it flexible. Because in memory space, if you want to explore new ideas, you really need to be flexible. If you're not flexible, you may actually miss out on a lot of the ideas. So this is one kind of study that higher level simulation and Ramulator, in this case, enables. Basically, this is from the Ramulator paper directly, this is a performance comparison of different DRAM standards. We didn't cover a lot of these, but I gave you some of the ideas. SALP is, for example, Subarray level parallelism. Basically, you slightly modify the DRAM architecture such that you can pipeline accesses to different subarrays. That's the key idea. How do you do that? I briefly talked about, as you can see, DDR3, DDR4, LPDDR, GDDR5, as you can see over here. You can evaluate all of these with different workloads. In this case, we evaluated it with 22 workloads, I believe spec workloads, with a simple CPU model. And you can see the characteristics of different types of memories. These are the timings. These are the rates in terms of mega transfers per second. This is the data bus, ranks per channel, bandwidth. So Ramulator can model all of these and some more. And as you can see, you can reach conclusions like this. These are, violin plots. That was what I was trying to remember. These are violin plots basically that show the performance improvement, instruction per cycle improvement, normalized to DDR3 of different technologies across the 22 workloads. The blue is the average improvement, and the red is the span, and the violin shows the distribution of the workloads. Basically, most of the workloads are here because of the shape of this violin over here, as you can see. So you can reach, in this case, it's just performance, but we actually power models, and we're going to add reliability models into this as well. But you can see that low-power DRAM is actually lower performance. It's slightly lower, 12% lower performance, LPDDR3 compared to DDR3. LPDDR4 is about 8% lower performance. Subarray level parallelism actually is high performance. It's about 19%. HBM, high bandwidth memory, in these workloads, it's about 27% average higher performance. That's 3D stacked technology with high bandwidth, as you can see. You can look at the parameters. That's significantly high bandwidth over here compared to DDR3. So you can actually reach these sort of conclusions. And I think this is very powerful to do. You need to have this sort of extensible simulation infrastructures. And there's more to do in this area, in my opinion. It's fascinating. And this is, I think, this sort of infrastructure is really necessary to evaluate ideas in a good way. So if you're interested, you can take a look at it. The source code is available. It's becoming better day by day, in my opinion. This actually, the motivation for this was the simulator that, not the motivation, but the history of this is the simulator that we wrote at Microsoft Research eventually turned into Ramulator over the course of 10 years or so. Now it's much more accurate, of course. So this is an optional assignment. If you would like to look at it, you can review the Ramulator paper. You can email me your review, or you can put it on hot CRP. If Roman is here, he was there somewhere. He can put it on hot CRP. I'll remind him. You can download it and run it, and you can actually compare. You can do the comparison for yourself. It's very easy to do this comparison because even the workloads are provided in the Ramulator repository. And this sort of assignment actually can get you quickly started in memory systems research. I provide this assignment to my students, and it's very quick to get started in memory system research in the architecture level. Yes?
You're comparing different DRAM technology, but what controller are you using to control it?
Yeah, that's a great question. I mean, yeah. Basically, we're using very simple scheduling policies in this case, like first ready, first come, first serve. But we're adapting to multiple banks. For example, HBM has many more banks than others. But yes, you could customize the controller to the technology as well. Should I move on? Okay. Okay. Okay, there are more suggested readings. I think I'm going to go over them very quickly. These are some more readings over here. This actually goes through the 3D stacked memory. I'd recommend that. I think we'll put up these readings on the website. Right, Roman? Okay, good. And DRAM refresh, we're going to cover some of these if time permits today, if it doesn't tomorrow. And this is the reading on simulating memory. And some readings on memory control that we may cover later on in the course. But you'll have all of these slides, and there are more readings that you can find. I think before I go into this next reliability part, maybe I'll cover this inside the DRAM chip part. I think this is going to be a little bit more fun. We're going to go even more lower level and make some of the things a little bit more clear, and then we're going to go into reliability. I don't know why this is becoming worse again. These are slides that my student Vivek prepared, and I don't want them to go wasted. He's used them for other purposes, but I like how they're done, basically. So basically, if you look at a real DRAM chip, it looks like this. And there are many different goals over here in the design, as you can see. I've listed some of them over here: cost, latency, bandwidth, parallelism, power, energy, reliability. And if you look internally, this is a bank. Basically, it's a chip that has 8 banks over here. And each bank has some number of subarrays. Let's start with the sense amplifier. I'm going to start bottom up again. Somebody asked, what is a sense amplifier? So sense amplifier fundamentally is an SRAM cell, but there's other stuff in there that I'm going to omit. Basically, you have the top part that's connected to the array, and you have the bottom part that's not connected. And you basically sense what's inside a cell and capture the value over here. It's a cross-coupled inverter. And you enable it or disable it. There's some circuitry. So in this case, there are 2 stable states. In this case, the sense amplifier has captured a logical 1, VDD. In this case, it's captured a logical 0, 0. So its operation is this way, basically. You have this VT greater than VB when it's not enabled. When you enable it, the sense amplifier essentially senses which one is larger, and as a result, amplifies this part, the larger part to VDT, and the smaller part to 0. That's all you need to know, actually, from an abstract view of sense amplifier. Now, we can go into the detail of the circuitry, but that's really not necessary. So DRAM cell, on the other hand, this is the empty state. It doesn't have any charge in the capacitor. It's a fully charged state. This has charge in the capacitor, and it has a logical 1. So this can be encoded as logical 0, and this can be encoded as logical 1. So basically, the key characteristics is it's very small. It cannot drive long circuits. Reading destroys the state. So you need to sense it, basically. So how do you actually get this information to the sense amplifier? That's essentially through the bit line. So let's assume that you have a charged DRAM cell. Whenever you activate a row, what the activate does is, there's an access transistor over here. It basically connects this access transistor, the switch, to the bit line. And once you connect this to the bit line, initially this bit line, the pre-charged state of the array is you have 1.5 VDD over here and 1.5 VDD over here, basically. That's the pre-charged state of the bank. Whenever you connect this charged capacitor to the bit line, what happens is this capacitor loses a little bit of charge, very little charge, because it doesn't store a lot of charge to begin with. And it basically perturbs this bit line by some amount. And at that point, you also enable the sense amplifier. Now, because of the operation that I said earlier, sense amplifier amplifies this to VDD and amplifies this down to 0. Now it's sensed the VDD. And once this is amplified to VDD, this gets stored back into the capacitor, as you can see. That's the operation. Yes? Partly CMOS, partly analog. Yeah, it's not. Yeah, it's really a mix. Yes.
You mentioned in the morning that depending on temperature, things may work faster.
Yes.
What is it here or elsewhere?
We're going to talk about that. Depending on temperature. Yeah, we're going to get back to that. Hold off. Yeah. Yes.
This diagram shows that actually while sensing you're not using the
Yeah, I just realized that also. Basically, while sensing, what happens is this should go down to 0. There's a bug in the diagram. Very good. In some other diagram, I think it goes down to 0, but somehow these animations are a pain in PowerPoint. Okay, so that should go down to 0. That's because there's very little charge and it gets lost very quickly, actually. You destroy the cell. Okay, so that's basically it. That's how you sense a DRAM cell. So DRAM subarray is a building block for a DRAM chip. Now let's actually build the subarray. So this is the sense amplifier, and this is one of the cells. You actually have many of these, as you can see over here. And this is basically the row. This is your column. This is your row. And that's the enabled circuitry. And you have a row decoder. And that's how you sense the cells. So you have an array of sense amplifiers, let's say 8 kilobits over here. You have cell arrays on both sides. And you have the bank I/O logic, basically. Okay, maybe we're going to simulate. You get an address. It basically gets fed into both of them, as you can see. You actually enable one of these and then read out of that. Let's go into that, actually. Let's go into how to read from a DRAM chip. This is 8 bits. the memory channel, and you have a bunch of these internally. And there's a shared internal bus between them that enables these 8 bits to go out. And let's look at the operation. So activation of the row basically activates an entire row over here. Let's assume that we want to read this one from the row. Basically, in this subarray, this row buffer gets enabled. And a row buffer is actually shared between 2 subarrays over here to keep the cost down. Now the row is activated, similar to what we've discussed. Now you can read or write a column. You send the column address, and the data gets out through the big global bit lines, through the spank I/O. And pre-charge is basically doing this, as we've discussed. And that's the end of the animation. So hopefully this this grounded a lot of the things that we've discussed so far. Any questions? There's a lot that goes into sense amplifier design that's really not the subject of the course. It could be very boring for many people over here. But that's true for many memory technologies. For, as I said, for any memory technology to work, that sensing circuitry needs to work. And that's becoming harder to design correctly in DRAM, with the charges becoming much smaller. Okay. So that brings us to backup slides, which means that we're going to switch to the next lecture. But feel free to ask questions while we're doing that switching, because this will take some time. How much time do we have? Oh, I think we've successfully killed the clock over there.
Until 5. It's 4 o'clock now.
Oh, okay, 55. So, okay, then I will continue.
You want to do a 5 minutes break? Then,
As long as it's 5 minutes, sure, yes. It's very hot here, I think.
5 Israeli minutes or 5
I think
Swiss minutes?
5 in Swiss minutes in this case. It's very hot here, isn't it? I think I need to, that's why we need to refresh more. So it's very fundamental, as you can see. When it's very hot, you need to refresh. Okay, 5 minutes.
French Swiss.